So, hello everyone. So, in last class, we have talked about the biopharmaceutics, and today we are going to start our discussion on the pharmaceutical analysis. So, every year, at least 10 questions are appeared in the GPAT examination from the subject of pharmaceutical analysis. And in the analysis, basically, the importance lies for the same while coming to the uh, JE NIPER also. So, first, us start our discussion with the introduction to spectroscopy. So, generally, the methods of analysis are very important while coming to the any pharmaceutical industry because whether it may be a API, excipient, a final product, all undergo a systematic evaluation and analysis by using the various methods. So, basically, the analysis is different types. Basically, a broad classification of analysis can be given by this ways. Basically, first one which includes the spectroscopical method. In spectroscopical method, we generally use the electromagnetic radiation. Electromagnetic waves, what is waves, well, everything we are going to discuss. So, first one is the spectral method where we are going to use the spectroscopic waves. The second method is the chromatographic method. The chromatographic method can be based upon many principles which may can include adsorption, partition, ion exchange, and also size exclusion, etc. Next, the third one is the electroanalytical. The electroanalytical includes potentiometry, conductometry, where a specific electrical property we study and we measure, which is related to the substance. Next, while coming to the physical techniques, biological and microbiological techniques also. And next one also radioimmunoassay. Radioimmunoassay are generally done in the diagnostic purpose. So basically, first of all, start our discussion to the spectroscopy. So basically, spectroscopy it all deals with the electromagnetic radiation, which is also known as EMR. So basically, the electromagnetic radiation. What are the two major components of the electromagnetic radiation? Tell me, guys. What are the two major components of the electromagnetic radiation? The electromagnetic wave is made up of two components. So can anyone say me what are those two components by which through which the electric field, electric wave and magnetic wave? Yeah. So both the electric and magnetic waves are perpendicular to each other. They lie perpendicular to each other at an angle of 90 degrees. So basically the electromagnetic radiation travels with the speed of light in the vacuum, and there are different types of electromagnetic radiation based upon their energy and wavelength. So there is a sequence of electromagnetic radiation. So most highest energy is possessed by which electromagnetic radiation, guys? Answer. The highest energy is possessed by which electromagnetic radiation? The highest energy or the lowest wavelength is possessed by which electromagnetic radiation? It is basically the gamma rays. The gamma rays possess the highest energy among the all available electromagnetic radiations, all the all available known electromagnetic radiation to the humans. So basically, every wave has some of the properties or the parameters through which those are measured. So basically, this is let us consider this as a wave. So basically, the upper portion is known as crest and the lower portion is known as trough. So basically, the distance between this difference between the stress crest and the trough. So basically, distance between the this and this. So is known as wavelength, and frequency is known as number of waves which travels to a particular point in duration of a 1 second. For example, we consider this as a 1 point. Then how many number of waves in 1 second travel through this point is known as frequency, any point. So frequency is basically inversely proportional to the wavelength. So a wave which is having the larger wavelength will have the smaller frequency. Next, wave number. So wave number specifically indicates the distance. So basically number of waves passed through a space of 1 centimeter. So for example, this is a space. For example, this is a distance of 1 centimeter, and how many waves are passed through a space of 1 centimeter is known as wave number. So wave number, the units are very important, guys. The these all about the units where the picture comes into the play. So wavelength units can be measured as meter, centimeter. So this distance can be meters, centimeters, micrometers, nanometers, and Armstrong. Frequency generally indicated in the terms of hertz and CPS, CPS and Fresnel. So in NIPER 2023, I think so they have asked about the unit of the frequency, but they have given the unit Fresnel. So you guys have to remember the frequency can be expressed as hertz, it can be expressed as uh, cycles per second Fresnel, and basically the wave number it is expressed as meter inverse, like a centimeter inverse in Teicher. So next, while and there is a relationship between the wavelength and the frequency and the energy. So basically, there is a classical equation which is known as E equal to hc by lambda. So I'm basically lambda. So E is equal to hc by lambda. So this is basically a classical equation. So from which we can determine the energy of any wave by knowing the wavelength, or we can determine the wavelength of any wave by knowing its energy. So E is equal to hc by lambda is very important. And another one equation which is very important, which is frequency. Frequency is equal to C divided by wavelength. So C is nothing but speed of light. Speed of light which is nothing but 3 into 10 power 8 centimeter per second. And this is frequency is equal to C by wavelength. So these two equations are very important, guys. You have to remember these two equations. And I think so every 2 to 3 years once they give the energy of any wave, and they try to estimate you the wavelength, and you have to guys calculate the wavelength of the given wave. So basically, based upon the what or which constituent in a molecule interacts with the wave, there are different spectroscopies have been classified. The first one is the according to the atom or molecule. So first one is the atomic spectroscopy. So in atomic spectroscopy, there is a change in the energy of an atom. So basically, the examples are the atomic absorption spectroscopy and atomic emission spectroscopy. In atomic absorption spectroscopy, we determine the absorbance, and in atomic emission spectroscopy, the amount of electromagnetic radiation emitted from the atom is measured, and each and every atom has the different emission spectra. Next, while coming to the second one is the molecular spectroscopy. So basically, a molecule is made up of group of atoms. So if you study at the atomic level, it is known as atomic spectroscopy, and if you study at the molecular level, it is known as molecular spectroscopy. So basically, the atomic spectroscopy includes the examples UV, IR, NMR, and atomic emission spectroscopy includes flame photometry, fluorimetry. So basically, as you guys have known that the each have the colors of the white light are the Vibgyor, where the violet, indigo, blue, green, yellow, orange, red. So basically, the violet has the shortest wavelength and higher energy. So as we go down, the wavelength of the wave increases and the energy decreases. So basically, let us start our discussion on the first one is the UV visible spectroscopy.
So UV visible spectroscopy is basically, guys, can you say me the range of the UV visible spectroscopy? What is the range of UV visible? Say me the range of UV visible, guys. What is the range?
200 to 800. So, and what is the range of the UV? Range of UV, only UV. So basically, UV stands from great, Satvik. So it is stand from 200 to 400, and from the 400 to 800, basically we talk about the, yeah, great guys, great. So we talk about the visible. So basically, UV region is also divided into many zones. So it is near UV zone, far UV or vacuum UV, visible UV. So basically, UV is only detected. I let I think you will have a preliminary idea about the UV. So UV is mainly used for saturated compounds, alkanes, aromatics, D all. Answer to this question, guys. UV is mainly used for the analysis of which type of compounds? Let me zoom it. Answer to this question, guys. Answer to this question. UV is mainly used for the analysis of the which type of compounds? Saturated, alkanes, aromatics, and all. So it's not on. B and C. Sorry. Hmm. Come on, guys. Answer. Answer to this question. Everyone, quick. So basically, most widely, most widely, B and C. Basically, saturated compound are not easily get excited by the normal UV range. They are generally falls in the vacuum UV, so that's why mostly used for the it's not BNC also only for the aromatics. So basically only aromatics unsaturated compounds are only get detected by the UV, and most probably the saturated compounds are generally difficult to detect by the UV because we have to use vacuum UV, and vacuum UV is very have the high energy, and it is have the very low wavelength. So basically, these I think so. You guys have the idea about this. So 1 angstrom is equal to 10 power minus 8 centimeter. 1 nanometer is equal to. So these are the basically typical units you have been known. So basically, in UV, there is a excitations of the electrons from the lower energy state to higher energy state. So lower energy state to. So this is the energy gap between the two states. This is the delta E. So this is the energy gap between the two states. And basically, whenever the UV radiations falls on a compound, the energy of the UV, when it get equalizes with the energy difference between the two states, it leads to excitation. So from lower energy state, which is known as HOMO. So let me type it. So from HOMO, the excitation occurs from the HOMO to LUMO. So HOMO is known as highest occupied molecular orbital, as we know that initially these are occupied by the electrons, and the LUMO is known as least unoccupied molecular orbital. So basically, this is a transition between the HOMO to LUMO. So transition between the HOMO to LUMO, and there are energy absorbed in the UV visible region produces a change in the electronic energy of the molecule, resulting from the transition of the valency electron of the molecule. So basically, I have mentioned that electrons are getting transferred from the HOMO to LUMO. So basically, there are different types of electrons which can be get excited by the UV visible. Are the first one are the
sigma electrons, sigma pi, and lone pair, lone pair electrons, which are generally denoted by the N. So basically, the sigma electrons, which is denoted by the symbol sigma, so these are get transferred from the sigma to sigma star, sigma to sigma star. So sigma star is denoted by this. So I will show you guys all the diagrams, and pi star and lone pair. So basically, the sigma, the transition between the sigma star requires more energy when compared to the pi star and pi n star, pi n pi star. So basically, the order is. Do you guys able to remember the order between the pi star and n sigma star and pi star? Do you guys know the order? If anyone knows the order of the energy required for the transition, please mention me. Please answer to my question. The transition order between the sigma star to n sigma star, n star, pi star, sigma star highest. Great. Next, after sigma star, first one is the sigma star. Next, n sigma star. Great. Next is highest than n sigma star. Nice. Great, guys. Next, next, pi to n. Is it pi to n or it is pi to pi? It is pi to pi. Next, it is pi to pi. Next, n to pi. Great, Kavish. Great. Next, it is n to pi. Last one. So, most widely occurring transitions in the UV are these two. These two mainly occur in the vacuum UV, and these two transitions mainly occur in the near UV or far UV regions, which is basically the visible regions. So UV spectra arises from the transition of the electrons or the electrons from the lower energy state to the higher electronic energy state. So the lower energy state electrons are also known as bonding electrons, and the higher energy electrons are also known as anti-bonding electrons. So there can be a transfer from the bonding to the anti-bonding. So basically the pi star transitions. So let us have the pi star transition. So pi sigma star. So let me. So basically the sigma star transitions. The sigma star transition requires high energy. Requires high energy and undergo requires high energy, and basically it occurs in the vacuum UV. So here you have to remember, guys, vacuum UV generally in the 150 nanometers. So it is basically which compounds show the sigma star transition, guys? Answer to the question. Which type of compound show the sigma star transition? Alkanes. Great, Kavish. Great. So basically shown by alkanes. Saturated compounds. Great, and we. So next, while coming to the N sigma star. So N sigma star falls in the near UV region. Falls in the near UV region, basically between the 150 to 200 nanometers, and it it occurs in which type of compounds? The N to sigma halogens. Great. Next, alkyl halides, alcohols, etc. Amines. Great. So next, pi star. The pi star occurs in aromatics, unsaturated compounds. All those compounds occurs in pi star, and the n pi stars occurs in the etc. compounds. So basically, another important about these transitions are there are another two types of transition based upon the energy, which are known as allowed transitions and forbidden. So basically, the allowed transitions have the
energy max, which is E max. How much energy, guys? Do you guys know? The yellow transition has how much energy? The E max energy. It is greater than 10 to the power of 4. It is greater than 10 to the power of 4, and and it is mainly due to the n pi transition, n pi star transition, n pi star transition. While the uh, forbidden transition has the E max of less than 10 to the power of 4, and it mainly occurs due to pi star transition. Pi star transition. So this is all about the types of transitions, and basically, do you guys have known the different bands which are absorbed in the UV? There are different types of bands which are absorbed in the UV. So tell me, guys, what is K band? What is K band and where it occurs? Come on, guys, quick. What is K band and where it occurs? Do you guys have any idea about the K band? Conjugate, right? So K band mainly occurs in the conjugated systems. So K band basically occurs in conjugate system like dienes, polyenes, enones, and aromatic compounds. So basically, the intensity of K band, the K bands falls under the category of alloy transitions. Alloy transitions. Next, R bands. These bands are very important, guys, because in the questions, direct questions are arised from the type of the bands. Next, R bands. Radiocalcic. So R bands occurs mainly due to the N pi transition, N pi star transition, and these transitions are basically forbidden. Next, B band. B band. So B band mainly occurs due to the pi star and due to in aromatics and benzonoids. Great. Aromatics. Next one is the E band. So E band mainly due to Italianic bonds. Due to Italianic bonds, the transition occurs. Mainly due to the Italianic bond, the transitions occur. So basically, these are the different types of bands which are absorbed in the UV. And another two important, most widely asked in the UV visible is the chromophore and the oxochrome. So what is difference between the chromophore and the oxochrome, guys? What is difference between the chromophore and the oxochrome? Do you guys have any idea about the chromophore and the oxochrome? What is chromophore and oxochrome? So basically, chromophore. So chromophore are the certain types of functional groups which show the absorption in the UV regions. Chromophore has the ability to absorb UV. Great, Grace. Due to the chromophore, the colors. Great, guys. I think so. You are able to revising your concepts. So chromophore are the basically compounds which are UV active. Is for unsaturated compound. Great. So basically, a compound which possesses a chromophore becomes UV active, and another and chromophore basically oxo is for saturated. Okay, so basically chromophore imparts a color to the compound, and a compound to be have a UV active nature, the chromophore helps in it. So chromophore are the certain types of functional groups which have the UV absorbance, and they impart color to the objects. So basically there are two types of chromophores. I think so you will have dependent chromophore. dependent chromophore and independent chromophore. Do you guys have any idea about these two? Do you guys have any idea about the independent chromophore and the dependent chromophore? So basically, independent chromophore are the chromophore which, when present as a single individual, they can impact the color. They, when they are present as individual, for example, N double bond O, N on NO2, N double bond N. So these, when they are present in a single in a molecule, they can impact a color. But while coming to the dependent chromophore, generally the color is impacted due to presence of more than one chromophore. So basically, the acetone having one ketone group is colorless, but acetone having two ketone groups give an yellow color. So basically, it requires a dependency of the another chromophore group to impact the color. So dependent chromophores are the type of chromosome where the two more than one chromophore required to impact the color to the compound. So basically, this is the difference between the chromophore and the oxochrome. Chromophore types, which is dependent and independent. Next, we'll coming to the oxochrome. Guys, could you say me, can anyone say me the different examples of the oxochromes? What are the examples of the oxochromes? Examples of the oxochromes. What are the different types of the oxochromes? Come on, guys, everyone, quick. OH, CHO. Great, great, guys. COOH, OH, SO3H, NH2, NH2, NHR, etc. So basically, uh, oxochromes are the, if these are the kind of groups which increases the conjugation in a system, and due to presence of these uh, oxochromes, there is an increase in the intensity of the absorption. So basically, this increases the intensity of the exochromes. So this is all about the basic concepts of the UV. So another most important law of the UV, basically which lays the foundation of the UV, is the Beers-Lambert's law. So Beer's law says that the intensity of the monochromatic light decreases exponentially with the increase in the concentration of the absorbing substance. Intensity, yeah. So the absorbance, the basically Beer's law states that the absorbance often a compound is directly proportional to its concentration. A more concentrated compound has the more absorbance when compared to the low concentrated. While coming to the Lambert's law, so when a beam of light is allowed to pass through a transparent medium, the rate of decrease in intensity with the thickness of the medium is directly proportional to the intensity of the light. So basically, the Lambert's law talks about the path length, and the Beer's law talks about the uh, Beer's law talks about the concentration, and the Lambert's law talks about the path length. So basically, according to that, next we also have to, every law has a certain kind of deviations. So we also have to remember the deviations of the Beers-Lambert's law, which includes that it is not applicable to concentrated solution, it is only applicable to diluted solutions, and law do not follow in case of suspensions, because in suspension there is lead to the scattering of the light in all directions, which may lead to the loss of the signal, and it does not obey if there is any chemical reactions in the solution. So if there is any transfer of the oxygen or anything, then in such situations we cannot apply the Beers-Lambert's law, and it is not used in the case of polychromatic light. It is only used for the monochromatic light. So what is meant by the monochromatic light, guys? What is meant by the monochromatic light? What is meant by monochromatic light? What is meant by monochromatic light, guys? Come on, everyone, answer it. What is meant by the monochromatic light? Light passes in the straight line. Monochromatic, I am asking the, what is the meaning? Yeah, only basically the wave which is having of the single wavelength.
It's not about, it is polarized and not, guys, you are getting confused between, yes, Shakshi, great. So basically, you are getting confused between the polarized light and non-polarized light and the monochromatic light. So basically, for example, we have the wavelength radiation from the 200 nanometers to 400 nanometers. Our source has emitted this range of radiation. So basically, the monochromator will allow only a specific wavelength of the light to interact with the compound. It may be 232, it may be 233. That's so the single wavelength of the light is known as monochromatic light, and the light which has the range of wavelengths is known as polychromatic light. So basically, this is how the whole formula. So basically, here you also, guys, you have to also remember the units and also the formula. So there has been a question in the GPAT 2021 regarding the Beer-Slambers law also, guys. So you have to remember the equation and also the whatever the units are very important, guys. So basically, A is equal to epsilon AL into C. So let me write here, guys, the equations or everything which we have to remember. So basically, A is equal to epsilon L into C. So basically, this is the equation. So while transmittance is equal to 10 power, it's minus 10 to the power of minus epsilon into C into L, 10 to the power of minus, and the absorbance which is denoted by the letter A is equal to 2 minus log percentage of T, where T is the transmittance and the specific molar extinction coefficient is denoted by E at the 1 centimeter length at the 1% solution, which is given by A divided by C into L. Sir, what is the unit of the absorbance? So let me have a, I think so I have a question for you guys. So unit for absorbance, A meter, B centimeter, C, maybe we can say that like molar inverse, D none, no units. So let us have a option no units. What is the unit for the absorbance, guys? None. So yes, great guys. So absorbance is a unitless quantity, and specific absorbance do not depend upon the concentration. So we also remember, guys, the absorbance dimensionless. Great, great, great. So great, Balaji. So absorbance depend upon the concentration, but specific absorbance do not depend upon concentration. The word specific whenever comes, it signifies that already predetermined. So absorbance depends on concentration, but specific absorbance is independent concentration. So this is very important line, guys, which you have to remember. The specific, the concentration and the specific absorbance do not depend upon that. So this you have to remember, the guys, and the wavelength. So basically, there are specifically shifts in the wavelength. So basically, generally we get the a graph between the wavelength and the absorbance in the UV. So basically, this is the graph. The wavelength at which the maximum absorbance occurs is known as. Guys, come on, answer. The wavelength at which the maximum absorbance occur is known as. The wavelength at where the maximum absorbance occurs. Lambda max, great. Lambda max, absorption maxima, great, great, great. So basically, what is meant by bathochromic shift? Bathochromic shift. Bathochromic shift. What is meant by bathochromic? Bathochromic shift. Higher wavelength. Yes. So shift towards the higher wavelength. So basically, it is a shift of the lambda max towards the higher wavelength. So it is known as bathochromic shift, which is also known as red shift. And there is another one shift is known as hypsochromic shift or blue shift, which is basically shift of the lambda max towards the lower wavelength. So basically, the red shift occurs due to the presence of oxochrome, and the blue shift occurs due to the removal of the oxochrome or the removal of the conjugation. So these are all the basic ideas. And next one, so let us go into the slide. So basically, the order of transition also I have discussed with you guys, the energy of the transitions and the types of the transitions which are mainly occurs. So this is another important types of the bands. So which I also have discussed. Next, also I have discussed about the chromophore, which denotes a functional groups, which gives a specific color to a compound. And nitro group is a chromophore, it gives a yellow color to the compound. Any group which exhibit the absorbance in the EMR radiation, it is known as chromophore, which is also mentioned. So basically, these are the different types of terminologies which have to be remembered to you guys. First one is the bathochromic shift, which involves the shift of the absorbance maxima towards the longer wavelength. Because in the presence of certain groups called oxochromes by changing the solvents or extension of the conjugation. So basically, the increase in the conjugation also leads to the decrease in the energy required for the excitation and increase in the wavelength. Next one is the hypsochromic shift. Hypsochromic shift is also known as blue shift. So it involves the shift of the absorbance maxima towards the shorter wavelength due to removal of the conjugation or by change of the solvent. So by addition of the conjugation, it leads to bathochromic shift, and by the removal of the conjugation, it leads to hypsochromic shift. So hyperchromic and hypochromic shift. So hyperchromic shift is basically increase in the intensity of absorbance. For example, this is the intensity of the absorbance, and by introduction of the oxochrome, there is an increase in the intensity of the absorption. Hypochromic shift, which is nothing but decreasing the intensity of the absorbance caused by the groups due to the distort the geometry of the molecule. So this is the basically choice of the solvent which have been used in the generally different solvents in which the. So let me frame a question here. Which solvent is not used in UV? So first one, water. Second one, ethanol. Third one, cyclohexane. D, benzene. Come on, guys. Answer to this question. Which solvent is not used in the UV? Come on, everyone must answer it. Everyone must answer to this question. The 30 people present. Yeah, great, guys. The benzene is not used as a solvent in the UV because the benzene itself also has a absorbance in the UV region. That's why it is not used. The solvent which is used should not have its absorbance getting overlap with the absorbance which is produced by the sample itself. Great, guys, great. So basically, let us also have another slide regarding the UV. So here we have where I have discussed everything about B.S. Lambert's law, which have is for the EA equal to epsilon CL. So Lambert's law, this is Lambert's law. So these are the basically the law states that there is a linear relationship between the there is a linear relationship between the absorbance and the concentration of the samples, and it relates to the attenuation of the light depends upon the properties of the material, chemical analysis measurements. So these are the etc. So this is basically where I have discussed it, that concentration directly proportional to the amount of light absorbed, inversely proportional to the logarithm of the transmitted light. So this is basically we have to remember. You have to remember, guys. So A equal to minus log I by I naught. So I naught is the intensity of the eh, incident light, and the I is the intensity of the emitted light. So which is known as I equal to I naught 10 to the power of EDC. D is nothing but the distance, the path length. So deviation also occurs, as I mentioned that there should then whenever a solution comes for the analysis of the UV, there must be no chemical reaction must occur in the during analysis, because the chemical reaction can also cause the deviation from the B.S. Lambert's law. So the chemical deviation can occur to the association, complex formation, dissociation, hydrogen bonding, hydrolysis, ionization, polymerization. So these equations can also cause the uh, deviation in the UV. So basically the hydrogen bonding. So due to the hydrogen bonding, there can be lead to decrease in the wavelength of the absorbance. So deviation caused by the polychromatic light. So we have to also use this monochromatic light. So basically the overview of the this is the basic instrumentation of the UV, where the different light sources are used. So what are the source of the light used in the UV? Guys, give me the examples of the light source used in the UV. What are the different light sources that have been used in the UV? Come on, guys. Xenon lamp, great. Hydrogen deuterium lamp, tungsten filament lamp. So these are the different. And next one is the dispersive, and we also consist of the monochromators. So monochromators can be prism or the gratings. So gratings. So basically, gratings are made up of the gratings are made up of the gratings which are based upon the principle of the diffraction. Good, good, Bharat. So basically, it follows the Bragg's law. So what is the material of construction of the gratings? The gratings are made up of aluminium. Great, Satvika, great. So basically, and the sample holder is made up of the quartz. Quartz is nothing but the fused silica. Great, Vivek, great. So glass. So generally, the sample cell can be used as a glass if the radiation is visible. And in the quartz, does the silica is in the amorphous form or the crystalline form? The quartz contains silica in the amorphous form or the crystalline form. Come on, guys, answer. In quartz, the made up of fused silica, the silica is in amorphous or crystalline form. In which form the crystal? It is in amorphous form. The silica is in amorphous form in the quartz. So this is the basic instrumentation of the UV. Here we can see that here we keep the reference cell and here we keep the sample cell. So radiation source, as I mentioned earlier, you guys have answered it. The hydrogen lamp, deuterium lamp, xenon discharge lamp, mercury arc lamp. So these are the basically different types of the lamps which have been used. So tungsten lamp mainly it is used for only the visible radiation. So it is similar to the functioning of the electrical light bulb. So here it consists of a tungsten filament. This is the filament, guys, which when gets heated emits a white light. So basically it emits the shorter wavelength of low intensity wavelength and constant intensity. So basically if you increase the electrical load on this bulb, the intensity of the emitted radiation also increases. So the other one is the hydrogen discharge lamp. So hydrogen discharge lamp is stored under the high pressure, and the electrical discharge through the lamp excites the hydrogen molecule and UV radiation. So basically here we provide the electrical current. Due to the electrical current, the hydrogen gas which is present inside the glass at the high pressure get excited and releases the radiation. So these are the different types of the lamps, xenon discharge lamp, where which you, and these are the monochromators. So monochromators has the basically three components: the entrance slit, the exit slit, and the dispersing element. So entrance slit, through which the radiation enters, the dispersing element, and the exit slit. So gratings have been used. There are two types of gratings, which is reflection grating and transmission grating. Generally, glass prisms. So prisms can be made up of glass, quartz, which is known as fluted silica. Glass prisms have the highest resolving power, but not transparent. Transparent between the 2000 to 3000 Armstrong. So basically, these are the different detectors which have been used, which includes the barrier layer cell, which is also known as photovoltaic cell, and the semiconductor like selenium deposited on the metal plates like iron, and the thin layer of the silver or gold sprouted over the surface and certain collector zone. So basically, different like photo multiplied tube, photodiode array. So these are the different types of detectors which have been used in the UV. So this is the photo cell. This is the photomultiplied tube, which consists of the many diodes. So basically, it consists of the diodes. So each it get multiplies. So by this, the signal get multiplies and can be used. So see, so it is a combination of the photodiode and electron multiplying amplifier. So it consists of a tube which consists of one cathode and 9 to 16 electrodes, which are known as diodes. So the electrodes are made up of anode. So dynode surface it is made up of beryllium, copper, or cesium, or etc. materials. So this is basically principle where we can see that it leads to increase in the intensity of the signal whenever the signal falls on the each dynode. And there are such a kind of 9 to 13 dynodes present in the photomultiplied tube. So this is the recording system. As I mentioned that there are the different shapes of the cells which have been present. These shapes are should be inert to the solvents, transmit light of the desired wavelength, and fused quartz or fused silica is the most widely used. So as you I think so in during your B form, you have also been performing the experiments under the subject of the instrumentation analysis, where you have been observed different types of cells. So next, another important concept while coming to the is the Beard-Lambert's law. So I think so you have been quite familiar, and you guys have been solved many questions regarding the Beard-Lambert's law. So basically Woodward Fisher rule. So basically here two important calculations are important in the UV. First one comes from the Beard-Lambert's law. So Beard-Lambert's law, a number of equations you have to guys remember, and based upon that you have to calculate the absorbance or the concentration. And the another one calculations which comes from the UV visible is the Woodward-Fisher rules. So basically, Woodward-Fisher rule is a basically rule which is mainly used to determine the absorbance of a given compound. So basically, there are the different values, base values, and the extra incremental values which have been given. So everyone do mistakes in this type of rules. So everyone must remember this rule correctly. The base value, the increments. So basically, for the acyclic conjugated diene. So basically, which is the acyclic conjugated diene or heteroannular. So here the two terminologies you have been get exposed, which is one is the homoannular and the heteroannular. So homoannular is nothing but the double bonds are present within the single system. For example, the benzene. And the heteroannular is nothing but a conjugation system where the double bonds have been shifted to the two different systems. So basically, these are the base value. So for the acyclic dienes, it is 215 or sometimes 217 nanometers. So homoannular conjugated dienes 253. So if in a ring both homoannular and heteroannular are present, so which one should be given priority, guys? If a ring contains both homoannular and a heteroannular conjugated diene, so which one must be given priority? Answer, guys. Answer to me. If a ring contains both homoannular and the heteroannular, which one must be given the priority? Homo. Great, Vivek. Great. So homoannular must be given priority, and this is the base value of the acyclic triene. So basically, each ring residue has the 5 nanometers, exocyclic double bond 5 nanometers, double bond with existing conjugation 30 nanometers, and these are the basically, if there are any specific functional groups, like if there is OR, then we add +6. If it is SR, then we add 30. Chlorine bromine 5, NR2 60, and OCO CS3 we add nothing. And if they mention the solvents, so basically these are also values. Come on, guys, answer to this question. What is the lambda max for this compound? Everyone must solve this question and answer to me. Everyone must answer to this question. What is lambda max of this compound? Take pen and paper and solve it. I think so. This is about the not this. So let us solve. Not this. Not this. Wait a minute, guys. Wait a minute. Solve this. Solve this. Solve this. Come on, guys. Everyone solve this question. Solve this. Everyone must solve this question and to answer me the lambda max. Come on, guys. Fast, fast, quick, quick. You have to solve any question in less than 1 minute. Come on, quick, quick. 253. Come on. Only Vivek has answered. What happened to other students? What happened to other 29 students? Come on, guys. I want everyone's answer. Guys, these kind of questions are only get mastered by only practicing. If you don't practice the Woodward-Fisher rule, you can't able to correct the answer. These are the best scoring questions. If you, still you have to know only the basic base values. If there are any ring residues or any exocyclic double bonds, then that's it. Come on, everyone. I'm waiting for you guys. Everyone must answer to this question. Come on. I have been only seen only one answer. What about others? Why others are can't able to solve this question? What is difficulty? This is the basic simple structure I have been given as an example to solve you guys. Okay. So let me say me what is the base value? What is the base value? What is the base value of the system? What will be the base value? 215. Great. So 215. How many ring residues are present in this? How many ring residues? Number of ring residues. Number of ring residues in the system. Come on. How many ring residues are present in the system? How many ring residues? 1, 2, 3. 3 5 is 15. 15. And is there any exocyclic double bond? Yeah. So for this system, this is exocyclic double bond. So +5. So it would be 235. This is what simple, guys. That's it. So this PPT would be shared with you guys. So come on, guys, answer to this question. What is the name of the instrument used to measure the absorbance of the colored compound in a solution? Come on, guys, answer to this MCQ. Everyone, everyone. I want everyone answers. Great. Colorimetry. Colorimetry. Great. In UV spectrophotometer, the sample cell is made up of. It's quartz. According to B.S. Lambert's law, of which of the following does the absorbance does not depend? Everyone must answer to this question. Everyone. I have only got two answers. 3, 4. It is the color of the sample. In UV spectrophotometer, the path length is normally. Come on, guys, answer to this question. The path length. I'm giving you a hint, guys. Once it is 1 centimeter. It is 1 centimeter. It is 1 centimeter. So 1 centimeter is equal to how many mm? Millimeter. 1 centimeter is how many millimeter? Ten. So the answer would be 10. Next. So that is for the all UV. Anyone has any doubts? So I have been shared PPT to the group. So you guys have to receive the PPT and you guys solve the other examples related to the B.S. Lambert's law. So is there any doubts related to the UV so that I can move to the IR? Is there any doubts related to the UV? Okay. So now let us move our discussion to the IR. So let me share the screen. So as I mentioned in the introduction, that this is very important, guys. So as I mentioned that as we go from the bottom to up, the energy of the wave decreases and the wavelength of the wave increases. So basically, spectroscopy as is a study of the interaction between the matter and the electromagnetic radiation. So these are the different types of spectroscopy these which are present in our syllabus. So as we discussed about the UV, so the IR spectroscopy basically it is a molecular vibration through the irradiation of the IR light. So basically the infrared light whenever falls on the molecule it leads to the vibration in the molecule. So basically whole IR spectroscopy is based upon the Hooke's law. So Hooke's law, based upon the Hooke's law, it provides. So IR spectroscopy is basically used for the fingerprinting of a molecule. So generally, the IR spectroscopy is used to determine the any functional groups present or absent in a molecule. So every molecule has a unique IR fingerprint. No two molecules will have a same IR fingerprint. And IR spectroscopy is very much important to identify the functional groups in the drugs, excipient, etc. So what is IR spectroscopy? So IR spectroscopy is a study of the absorbance of the IR in radiation which causes the vibration transition of the bonds in the molecule. So it is called vibrational spectroscopy. So IR spectroscopy nothing but whenever a IR falls on the molecule, they lead to vibrations produced in the molecules. So basically in UV where we have mentioned the absorbance. So in IR we plot a graph between the wave number and percentage transmittance. So percentage transmittance and the wave number, which is basically indicated by the centimeter inverse. So IR spectroscopy, as I mentioned earlier, is mainly used to identify the functional group, but also gives the idea about like number of bond, specific stereoisomer, atomic arrangement in the molecule. So these all information is provided by the IR spectroscopy. So basically, these are the main three broad applications of the IR. So basically, detection of the hydrogen bonding, studying the progress of the reaction, and determine the structure of the molecule. So which is the another technique which is used to detect the hydrogen bonding, guys? What is the another technique which is used to detect the hydrogen bonding? Can you guys able to remember? NMR, great Vivek, great Kavish, great. So NMR is the another technique which is used to detect the hydrogen bonding. So basically, as we know that the molecules are made up of the atoms, a group of atoms, and a atom never stay in a static way. It is in a continuous motion or the natural vibrations. So our atoms generally are in the natural vibrations. They continuously vibrate. But when we apply the IR frequency is equal to the natural frequency, which is nothing but the frequency of their vibration, it leads to the absorbance of IR, and which leads to vibration at many rates, and we get the IR spectra. So basically, this is the whole principle of the IR. So the IR frequency matches with the vibrational frequency of the molecule, and the each functional group has the unique vibrational frequency by which the each molecule has a unique IR spectra. So basically, another most important requirement for a molecule to be IR active is, guys, can you able to remember which is the most important criteria for a molecule to be IR active? If anyone can able to recall this, the most important characteristics of a molecule to be an IR active molecule. I need a change in dipole. Great, Vivek, great. So yeah, great, TG, great. So basically, there must be a dipole present in a compound, so that then only it may be the then it only be the IR active. Great. So infrared energy radiation is largely thermal energy, and it induces the strong molecular vibrations in the covalent bond, which can be viewed as a spring holding together as a molecule. So basically, whenever a IR rate, so basically this is the equilibrium. So every bond has a specific stretching frequency or the vibrational frequency. No two molecules have the same vibrational frequency. So whenever the IR radiation of that frequency falls on a compound, they lead to change in the vibrations, which leads to the bond length or bond angle changes. So where we are now going to discuss about the further. So these are the various vibrational levels which are present in our molecule. So basically, this we have to remember. So energy of the vibration is equal to V plus half h mu. So V is the vibrational quantum number which can range from 0, 1, 2, and h is the Planck constant. So value of Planck constant is also very important, guys, which is 6.63 into 10 power minus 34. And delta E of the vibration, so E is equal to h mu, so this gives the frequency of the number of fundamental bonds. So basically, uh, the IR is also divided into the three zones: near IR, mid IR, and far IR. So basically, so the near IR, so near IR has a range from the 0.8 to 2.5 micrometer. The mid IR has a range from 2.5 to 15 micrometer, and far IR has a range from 15 to 25 micrometer. So these are the basically important wave numbers which you have to guys remember. So here the another quite important concept which you have to remember, guys. So when IR radiation interact with the sample, the sample molecule absorbs the specific applied quantized IR light of the specific frequency when it get matched with the internal vibrational frequency of the molecule and the other resident frequency are transmitted via the sample. So due to the absorbance of the IR radiation, there is a net change in the dipole moment of the molecule is occurred, because due to the vibrations in the molecule, there is a net change in the dipole moment. That's why the molecules which do not possess any dipole moment are IR inactive and causes the vibration of the bonds in the molecule like stretching and the bending vibrations by the detector, and the IR spectrum is interpreted by the computer skin. So this is the basically principle of the IR, where a basically IR radiation falls on a sample. The sample only absorbs the IR radiation when its vibrational frequency matches with the incident IR frequency, which leads to change in the position of the atoms in the molecule due to net change in the dipole, which changes and leads to transmitted light. So basically, here we use the wave number. Wave number, as I mentioned earlier, which is equal to 1 by lambda. So frequency is equal to wave number into C, which is nothing. So wave numbers are directly proportional to the frequency. So basically, as I also understand, the IR reagents is divided into three types. So based upon the near IR wavelength, 0.8 to 2.5, 2.5 to 50, 50 to 100. So basically, these are the different regions of the IR. So basically, another two important types. So basically, the whole IR, rather than dividing into the near, mid, and far IR, it is also divided into functional group region and fingerprint region. So basically, the functional group region lies from the range of the 4,000 to 1,500 centimeter inverse, while the fingerprint region lies from the 1,500 to 600 centimeter inverse. So while coming to the functional group region, the most functional groups present in the organic molecules exhibit the absorbance band in this region only. So whatever the functional groups, whether it would be aldehyde, ketone, ester, amide, imine, all these wide variety of the functional groups which are present in an organic molecule, those all lies in the functional group regions. So in this region, so two molecules, if they have the same functional group, then they would have the same functional group region spectra. So in this region, each band can be assigned to the particular deformation of the molecule, the movement of the group of atoms, or the bending or stretching of the particular bond. While coming to the fingerprint region, so as I mentioned earlier, the two molecules can have the same spectra in the functional group region, but they would have a different spectra in the fingerprint region. So fingerprint region can be used to identify a particular compound. So the region between the 1,500 to 600 in the IR spectrum is known as fingerprint region. And in this region specifically, the bending vibrations are the more when compared to the stretching vibration. So this you have to remember it, guys. In fingerprint region, the bending vibrations are the more prominent when compared to the stretching vibrations. So now answer me, guys. For which type of vibrations it requires more energy? For the bending vibrations or for the stretching vibrations? For which vibrations it requires more energy? For stretching vibrations or the bending vibrations? For which type of vibrations it requires more energy to induce the vibrations in a molecule? It is basically the stretching vibrations. Stretching, great, Sujana. So basically, for the stretching vibration requires more energy when compared to the fingerprint region. That's why the number of molecules contain the same functional group show the similar peak above 1,500, but they show the different peak in the fingerprint region. So therefore, we can say that each and every molecule has a unique peak or band which is observed in the fingerprint region. It's like a fingerprint of the human. See, guys. So this is basically the IR spectra of the two compounds, which is nothing but the propan 1 all and propan 2 all. So basically, as I mentioned earlier, it is basically the y-axis consists the percentage transmittance and the y-axis contains wave number. As you can see that the functional group region is same for the both compounds because both contain the same functional group, which is the OH. But while coming to the fingerprint region, it is different. It is different from the one propanol. It is different for the two propanol. So see, so both compounds are the alcohols and contain the same bonds. Now, if you compare the IR spectra of this compound, the functional group region is very similar to the both compounds, but the fingerprint region is totally different. I hope you guys have understand this. Next, while coming to the type of the molecular vibrations which have been seen, first one is the stretching vibrations and second one is the bending vibration. So basically in stretching vibrations, the interatomic distance is increased or decreased. So basically let us consider these two atoms. So in stretching vibrations, there can be a asymmetric stretching or symmetric stretching. So what is meant by asymmetric stretching, guys? What is meant by asymmetric stretching? Come on, guys, answer to my question. What is meant by asymmetric stretching? And in bending, they basically the opposite direction. Great. There is an increase or decrease in the wavelength in opposite direction. And bending is basically change in the bond angle between the bonds with the movement of the group of atoms. So as I mentioned earlier, bending is also called as deformation. Great. So basically, and the which law applies for the deformation? Which law applies for the deformation? Which law? There is a law. There is a law. Hooke's law. Great, Vivek. Great. So basically, the stretching vibrations, as I mentioned earlier, occurs at the higher frequency, and the bending vibrations occurs at the lower frequency. So asymmetric stretching and symmetric stretching. In symmetric stretching, there is a increase in both sides, or there is a decrease or increase in the both sides equally. While in the asymmetric stretching, one side is increasing and another side is increasing. While coming to the bending vibrations, it can be in plane bending or out of the plane bending. So scissoring. So scissoring is nothing but both molecules are coming towards each other, which leads to decrease in the bond length. While the rocking, is there any bond angle change in the rocking? In rocking, no. Great. So both molecules move in the same direction. So, for example, so both molecules move in the same direction. So there is a no net change in the bond angle. Next, out of the plane is the twisting and wagging. So, so generally remember it, guys. The number of bending vibrations are more when compared to the stretching vibrations. So, as I mentioned earlier, this is the basically whole schematic diagram of the stretching, rocking, scissoring, twisting, and wagging. As you can see that in twisting, one atom is above the plane and another one is the below the plane. The change in angle between the plane, two groups of the atoms. So while coming to the wagging, the both atoms are moved to the one side of the plane and changing angle between the plane of the two groups. So basically, in a molecule, there are different modes of there are different modes in the changes. So basically, in a molecule, three modes exists. So which is equal to translation motion, rotational motion, and vibrational motion. So we should know about the degrees of freedom. So the total degrees of freedom that can exist in a molecule is equal to transitional plus rotational plus vibrational. So which is basically, or vibrational degrees of freedom is equal to 3n minus transitional rotational. So basically vibrational degrees of freedom is equal to 3n minus 3 plus rotational degrees of freedom. So for linear molecule, it is 3n minus 5. For non-linear molecule, it's 3n minus 6. See guys, for CO2, CO2 is linear or non-linear guys? CO2 is a linear molecule or non-linear molecule? CO2 is a linear or non-linear? Linear. That's why it applies the formula of 3n minus 5. Yeah, great. So where n is equal to number of atoms present in a molecule. So CO2 has a 2 oxygens and 1 carbon. So 3 into 3 minus 4, it's 4. So as I mentioned, the criteria to absorb the IR radiation. Sir, for a molecule to show the infrared, it must possess a specific feature which is known as electrical dipole moment, which must change during the vibration. So basically, so during vibration, there is a change in the electrical dipole. And dipole, which is as you also known as the charge into different charge into distance between the charge. So in homonuclear diatomic molecules, these do not absorb IR radiation because there is a lack of uh, which is the lack of the dipole moment. So basically, some of the polar bonds can absorb. So this is symmetrical stretching, anti-symmetrical, in-plane bending, out-plane bending, so etc. These are the etc. So there is another formula which can be used to calculate the number of the vibrational frequency, which is nothing but V equal to 1 by 2 pi C into root over K by mu, where K equal to force constant. So basically, the stretching frequency of C triple bond C is greater when compared to C double bond C and C single bond C. So these are the basically force constant of the triple bond, double bond, and single bond. As you can see that the triple bond has the 3 bonds. That's why the stretching force constant is 15 into 10 power 5 dyne per centimeter. For double bond, it is 10 into 10 power 5 dyne per centimeter. For single bond, it is 5 into 10 power 5 dyne per centimeter. So as the stretching, so larger the K value, the higher would be the frequency. So larger the atomic masses, the lower would be the frequency. So here we can see that the CH and when compared to CBr, the bromine has the larger structure, larger atomic mass, by which it would have the lower stretching frequency. So basically, as I mentioned earlier, the IR spectra is basically plot of the transmittance frequency versus intensity of the absorbance. So these are the basically graph. The most widely used graph is this. So as I mentioned earlier also, the IR spectra, what is the importance of the functional group region and the fingerprint region. So the functional group region, the peaks are the sharp, broad, and strong and medium peaks. So these type of peaks are absorbed in the functional group region. So while coming to the fingerprint region, the sharp and weak peaks are absorbed. So basically, fingerprint region specifies each for the each and every compound, and each and every compound has the different fingerprint region. While the two compounds having the same functional group region due to presence of the same functional group can have the different fingerprint region. So basically, in functional group region, only stretching mode of vibrations. So it contains only few peaks. While coming to the fingerprint region, both stretching and bending vibrations are seen. And the pattern of the peak is more complicated because there are many different types of stretching have been seen in the fingerprint region, so which is difficult to interpret it. While coming to the functional group region, the pattern of the peak is easy to analyze because stretching vary within the narrow range. So basically, sometimes due to the hydrogen bonding or presence of the water molecule, there can be, this is the sharp peak, while due to the presence of the water molecule, there can be lead to the broad peak. So broad peak mainly occurs due to the presence of the hydrogen bonding or the water molecules. So basically, if there is a more electronegative difference between the two atoms, then there will be the more polarity, then there will be the more dipole moment, and the more intense peak will be going to be absorbed. So here you can see, guys, there is a broad peak has been observed due to the presence of the hydrogen bonding on the water molecule. So these are the different intensities of the peak. So these are the other factors which influences the vibrational frequency. So reduced mass, as I mentioned, like the larger the molecular mass, the lower will be the vibrational frequency. So force constant, conjugation or resonance is directly proportional to the vibrational frequency. Hydrogen bonding has the inversely proportional ratio. Multiplicity of the bond, number of bonds increases, then the vibrational frequency also increases. If the electronegativity increases, then also the vibrational frequency increases, and also the hybridization. So as we know that the percentage S character increases, then the electronegativity increases, then the bond strength increases, bond length increases, and the frequency increases. So these are of the different. So basically, another most important concept here is the sample preparation. So basically, so while preparing sample for the 1 minute, guys. So basically, the radiation source which is used in the IR. Guys, could you say me the radiation source which is used in the IR? Which radiation source is used in the IR? Radiation source. Deuterium, zirconium, great. Nunnest floor lamp. Nunnest floor lamp. Nunnest floor lamp, which is generally made up of the oxides of the zirconium, yttrium, erbium. And another one is the globular source. Globular source. Globular source is another source. Another one is the mercury arc lamp. Arc lamp is also used. So basically, uh, globals are made up of silicon carbide, grade, Kavish grade. So basically, another most important is the sample preparation. So whenever we try to prepare the samples for the IR analyzing, so we can analyze both solid, liquid, and gas samples. So both three states of matter can be analyzed by the IR. So basically, in solid, the most widely used is the KBr, potassium bromide, KBr or NaCl salt. So basically, these are the IR neutral compounds. These do not possess that much IR absorbance. So basically, we take our solid sample and we mix with the KBr and the NaCl or NaCl, and then we analyze it. So KBr and NaCl are used as dilute to prepare the pellets because these are the transparent for the IR radiations. And another one is the Mullin technique. Guys, in Mullin technique, which oil is used? In Mullin technique, which oil is used? Mineral oil, which is nothing but the liquid paraffin. Liquid paraffin. So basically, we prepare a paste with the oil and we spread it on a plate. We spread it on a plate, and this plate is go for the IR analysis. So next, the liquid and the gas samples are also analyzed by the IR by using the different techniques. So basically, do you guys know that which materials are used for the calibration of the IR? Calibration of the IR. Calibration of the IR is done by. Do you guys know how the IR is calibrated? So basically, the IR is calibrated by using 1 minute, guys. So IR is calibrated by polystyrene or water vapors. So another most important thing while coming to the IR, Most important thing while coming to the IR is the different types of detectors used in the IR. Come on, guys, say me what are the different types of detectors are used in the IR? Come on, bolometer. So basically, bolometer, it is based upon the Wheatstone beads. It consists of Wheatstone beads. Basically, when the IR radiation falls, the temperature increases, which leads to increase in the resistance. Resistance increases. So another one is the thermocouple. Thermocouple. So in thermocouple, there is an increase in the temperature between the junction. Basically, it is made up. The junction is made up of bismuth and antimony. So next detector which is used is thermistor. Thermistor which is made up of the fused metal oxide, and there is a decrease with increase in the temperature. Reverse of the bolometer. Next, third one is the Gole detector. Gole detector, which is consists of which guys? Do you guys know which gas is present in the Gole detector? In Gole detector, which gas is used? Inert gas. So basically, xenon is filled in this. Xenon gas is used. Next one is the photoconductivity detector. Photoconductivity detector. Generally, photoconductivity detector. Next detector is the semiconductor detector. So basically, these are the different types of detector which is used in the IR. So and also due to the hydrogen bonding, there is a shift of the wavelength towards the lower end. So basically, due to the hydrogen bonding, and you guys, you have to also remember the different stretching frequency of the different. Do you guys know the stretching frequency of the CHO? Aldehyde group stretching frequency. The stretching frequency of the CHO. Stretching frequency of the CHO. 1725. So basically, yeah, 1740 to 1720. So for the alkene, primary alcohol, secondary alcohol, tertiary alcohol. So these all you have to guys remember, because these are the very important and will come in the examination also. So do anyone has any doubt up to now in UV and IR? Any doubts up to now? Any doubts? Any doubts up to now, guys, in UV and IR? Okay, so that is for today, guys. So in next class, we're gonna discuss the other analysis technique. So I hope you guys have been preparing well for your examinations. So all the best, guys. So let us meet in the next class. Thank you, everyone.